This is the first lecture from Chapter 17, and this lecture will focus on buffer systems. General definition of buffer is a solution that resists changes to pH. Probably the most common system you're aware of is an in-ground pool where chemicals are added to keep the pH at a certain level. A buffer is made by mixing together both a weak acid and its conjugate base, or a weak base and its conjugate acid. But you do have to have an acid and a base present. They do have to be weak, and they do have to be conjugate pairs. And that's because they go back and forth from the conjugate acid to the conjugate base. That's how a buffer works. So just kind of a visual of what I said. When you make a buffer, you have to have both the weak acid and its conjugate base present, and they are in equilibrium with each other, and that's again how the buffer works. And remember that you can make a buffer either from a weak acid and its conjugate base or a weak base, which most of the time is neutral nitrogen-based compound. Remember, we call these amines, and ammonia is a very common one. So can also be a weak base and its conjugate acid. So how do buffers work? So it's probably easiest to describe using this visual. So if you have a buffer system made up of the weak acid, acetic acid, and its conjugate base, the acetate anion, and you contaminate it with either an acid or a base. So in this case, we're going to contaminate it with a base, hydroxide, let's say. And in this case, if you contaminate it with a base, the weak acid that you have made the buffer from, in this case acetic acid, is going to gobble up the contaminant base that got added, and in doing so is going to produce more of the conjugate base that makes up the buffer. So as a net result, you're going to end up with a little bit less of the conjugate acid than you started with, and a little bit more of the conjugate base that you started with. But because they're weak and because it hasn't changed it by much, the pH of the overall system will not change very much. If you'd rather look at this disruption to a buffer system using a chemical equation, this is how you would describe that. If you add a contaminant base, which again we're representing with hydroxide, to the buffer system, that contaminant base is going to react with the weak acid that makes up the buffer, in this case acetic acid, and it's going to produce more of the conjugate base, conjugate pair that makes up the buffer. Similarly, if you contaminate a buffer system with an acid, and we're going to designate that just by showing a hydrogen ion, the part of the buffer system that's going to chew up contaminant acids, obviously, is the conjugate base part of the buffer. And as a result of that, you're going to end up with a little bit less of the conjugate base in the buffer that you started with. And because the combination of the contaminant hydrogen ion and the conjugate base react to give you more of the weak acid, you're going to end up with a bit more of the original conjugate acid that makes up the buffer. And here is a chemical equation to represent that. And I know that you had a lab where you did something similar to this. All right, so how do we calculate the pH of a buffer system? Both initially, like when we first make the buffer, how do we know what its pH is? And how do we calculate the pH after we have disturbed a buffer system, either by adding contaminant acids or contaminant bases? The bottom line, what I want you to know off of this slide is this equation. Okay, this is called the Henderson-hasselbalch equation. And this equation is all you need to know when you're calculating the pH of a buffer system. I will not ask you to derive it, but it's very simple to see where it comes from. If you look at a generic chemical equation for a weak acid reacting with water, and you look at the expression for the equilibrium constant for a weak acid and rearrange it, okay, so that instead of having Ka off to one side, you have hydronium concentration off to one side. And then if you take the P of both sides, remember what P means? That little P is the same thing as saying minus log, okay? So if you take P of both sides, you end up with the Henderson-hasselbalch equation. So you need to commit this to memory, and it's actually very easy to use. Your textbook and some other sources will suggest that you calculate the pH of a buffer system using very complicated equations. You have my permission to ignore all those sources and simply use Henderson-hasselbalch. It will work for you. So one thing I want to point out that saves a lot of time when you're using Henderson-hasselbalch, notice that this ratio, this is the weak base that you have present in the buffer, and the denominator is the weak acid that you have in the buffer. So base goes on top, acid on bottom. But since it's just a 1-to-1 ratio, units cancel, and so you can use concentration units of the weak acid and weak base, like the equation suggests, or if it's easy, you can simply use moles of the weak base and weak acid if that's easier, because units cancel out anyway. All right, one other thing I want to point out about the Henderson-hasselbalch equation is that I want you to think about this ratio. What happens when you have exactly equal amounts of the weak base and the weak acid in a buffer system? So let's say you have 1 molar solution of each. What happens to this equation? Well, anytime this ratio equals 1, then of course log of 1 equals 0, and your Henderson-hasselbalch equation simplifies to pH equals pKa of the weak acid you have used to make up the buffer system. That's a really good way to find out what the pKa of a system is make the concentrations of the weak acid and weak base the same, and then measure pH. That will automatically give you pKa. All right, a couple of easy facts about buffer systems and what makes a good buffer, and then we'll work problems. So the best buffers have equal concentrations of both the weak acid and its conjugate base, so that it can handle contaminations of either acids or bases. And so this is just another way of saying the same thing. You also want a significant concentration of the weak acid and its conjugate base, so that you don't overwhelm the buffer system. So the higher the concentrations of the weak acid base, the more effective the buffer will be. And probably most important and possibly trickiest to understand, when you're choosing a weak acid or a weak base to make a buffer system, you want to choose an acid whose pKa is closest to the pH that you want the buffer to stay at. Okay, so make a note of that. Make sure that you highlight it to understand that. When choosing the best buffer, you first want to know whatever pH you want to control that system at. So let's say you want a pH to be maintained at around 5. That means you need to pick a weak acid whose pKa is closest to 5 as you can possibly get. It is okay to vary pKa by plus or minus 1 unit, but no more in order to get an effective buffer. All right, so here's a sample problem. You need to, first of all, get used to identifying buffer problems. You will not always be told you're dealing with a buffer, and so it might not occur to you that you want to use Henderson-hasselbalch. So you always, if you have a two-component system like you do here, you always want to ask yourself, are they conjugate pairs? If they are conjugate pairs, then you have a buffer system, okay? Conjugate pair means buffer system. And so you might ask yourself, okay, this is a weak acid, right, HCN, but how do I know that NaCN is its conjugate base? Well, another thing you need to get used to is when you see a salt, remember that's a nickname for an ionic compound, remember what salts do in water. They break up into the cation and the anion. And so now I'm hoping that you can see that once you break it apart, that the anion from a salt is actually the conjugate base of a weak acid. And so anytime you add conjugate pairs to make a buffer system, one of the components is almost always a salt, because a salt is the source of the conjugate base. All right? So anyway, now that you recognize this is a buffer system, you simply used Henderson-hasselbalch equation and plug in the values to calculate pH. This kind of goes over what in a little bit more formally than I just did in the last slide. And of course, you're going to need the Ka. All right, so now plugging the values into Henderson-hasselbalch, just a reminder. And I do want to mention at this point, too, that there are different forms of the Henderson-hasselbalch equation. Some of them have POH, some have PKB. I have noticed from my years of teaching that when I introduce multiple forms, students get confused, end up memorizing a mishmash of them and making mistakes. So my suggestion to you would be to always use this form of the Henderson-hasselbalch, commit it to memory, and pretty much ignore the other forms that you see. If you want to take it upon yourself to learn all the forms and understand how they're different and why, that's awesome. Okay, it's just more of a cognitive load for you. All right, so plugging in, we're trying to solve for pH. We know that P of anything means minus log, right? So minus log of Ka, which was given to us, plus log of the concentration of the conjugate base, that would be the sodium cyanide, that was given as 0.2 molar, divided by concentration of the weak acid, which is HCN, 0.5 molar. And when you plug that into your calculator, and I suggest you go ahead and do that right now to make sure that you're using the calculator you're going to use on the test correctly, because you will have a lot of Henderson-hasselbalch on this test. So the pH is 8.91. One little thing, if this makes sense to you and helps you, great. If it confuses you more, please ignore it for now. But kind of a check for yourself, remember that the best buffer systems have pH values that are very close to the pKa value, all right? And so when you calculate the pKa value, and remember that the log values are simply an expression of the exponent, the pH you get should be very close in value to the pKa value. So if you find pKa or minus log of this, you'll find that it's within plus or minus 1 of the calculated pH. That's just kind of a check for yourself. So I mean, let's say if you got a pH something like 4, 4 is so far away from 10 that you probably made a calculation error. All right, here's another one, and this is a buffer made from a weak base. Instead of a weak acid, it's made from a weak base and its conjugate acid. And again, this is a salt, an ionic compound, right? And so to get used to the purpose of that, remember to go ahead and dissociate them into the cation and the anion. And hopefully then you can recognize that this cation is in fact the conjugate acid of the weak base, ammonia. And so again, you're looking at a buffer system. You need Henderson-hasselbalch, and at this point, it is plug and chug. There is a trick waiting for you here, so I'm wondering if you noticed it yet. So here we go. The trick is that if you're going to use the form of the Henderson-hasselbalch equation that has pKa, you need Ka. And this problem gave us Kb. So the first thing you want to do is convert the Ka to Kb. And here it is. Convert the Kb to Ka. So here's Ka, which you need for the form of the Henderson-hasselbalch we use. Take the pK, the minus log of that. And remember that the base form of the conjugate pair always goes in the numerator. Okay? And that is 0.4. And concentration of the conjugate acid, 0.1, goes in the denominator. And now we get a pH of 9.85, which again is quite close to the exponent 10. Here's another one. And here's one that I want you to try. Okay, it's a little bit of twist on words, and that's always what makes these word problems difficult, is how you word them, I think, and can solve for different things. So in this case, let me give you a hint, and then I would suggest you turn off the video and try to work it yourself. Calculate the moles of sodium acetate. Okay, remember what I said, salts are a source of the conjugate. Okay, so what they're trying to get here is C2H3O2 minus. That is the acetate ion, okay, which serves as a conjugate base in this case. So they want you to figure out the moles of the conjugate base, right, that must be added to acetic acid, which is the weak acid, okay, in order to prepare a buffer with a pH of 4.68, and they gave you the Ka. So my hint is, what are all the pieces of information that you have given? Okay, so you've been given pH. You can quickly and easily calculate pKa. You have been given the concentration, or you can use moles, remember, of the weak acid, acetic acid, and you're solving for the concentration or moles of the conjugate base. I would recommend working, you may remember, hopefully, that I said since you have a ratio, a 1-to-1 ratio in this equation, that you can work in units of moles of each of them instead of molarity, instead of concentration. And since this problem is asking for moles, I would recommend working in moles for this ratio. So how do we figure out moles of the weak acid that we're given? So just kind of a reminder, if you have molarity, that's volume. If you have volume times molarity, you will get moles. Okay, liters cancel. All right, so we can easily find the moles of the weak acid acetic acid. It's 0.040 moles. That would go in the denominator here. And then working out the rest of the problem, plugging in what we know. pH was given to us. We can easily calculate pKa. It's a minus log of the given Ka. We just calculated the moles of the weak acid, and we're trying to solve for moles of the weak base, the acetate ion. So be really careful when you are simplifying Henderson-hasselbalch equations. It's very, very common to mess up. So listen really carefully to me now. This term, this pKa term, if you want to move it to the other side, you must subtract it from both sides. For some reason, a lot of you want to divide it, but no, it's an addition, subtraction thing. So in order to get rid of it, you need to subtract 4.74 from both sides, okay? And that's always the case for that pKa term in Henderson-hasselbalch. So when you subtract that from both sides, you get minus 0.06 equals log of this thing. Now you need to get rid of log. How do you do that? Well, it's log base 10, log log. So it's 10 raised, you raise both sides as an exponent to 10. When you have 10 raised to anything log, it cancels out the log value. And so now you have 10 raised to the negative 0.06. Okay? Now, in order to get the moles of the base, you have to multiply both sides by 0.040. And even if you haven't tried to work this on your own, I strongly suggest you get out your calculator and make sure that you get the value for the moles of acetate that I'm going to show you on the next slide. Again, to make sure you're using your calculator correctly, you've got to find that 10 to the x button and make sure you enter the negative sign correctly. All right, so when you solve that, you get that the moles of base, so this is the moles of the acetate ion, is 0.35 moles. That is the quantity of acetate you need to add to this buffer system to get the desired pH. Alrighty, so those are straightforward buffer problems, and I always kind of like to rank difficulty. That I would rank at a C level. You need to work those out just to get a C on this next test, which can be a little intimidating, but you'll get it. You just need to work a lot of problems, please. All right, so now what if you have contaminated a buffer with an acid or a base? That means you have two calculations to do to solve the problem. The second and last calculation is what we've just done. That's using Henderson-hasselbalch, which is the easier part for the most part. But before you can do that, you need to do a stoichiometry calculation, because think about it. If you have added a contaminant, you need to figure out first how many moles of contaminant have you added and how many moles of the buffer has that contaminant chewed up before you use the Henderson-hasselbalch. So here's an example I'm going to walk you through. And this is very likely one of your free response problems on your next test. Calculate the initial and final pH when 10 milliliters of this strong acid is added to just water, okay? So there's no buffer system in part A, okay? And the reason is, and I think that was in your lab too, is to get an idea how much pH will change. If you just dump a strong acid or a strong base in a system that's not a buffer, you're going to get wild pH variation. On the other hand, if you add even a strong acid or base to a buffer system, you're going to get a real small pH change. So buffers are really cool systems. So this is just a comparison. I'm going to talk for a minute about part A, because now that we start working on these complex buffer problems, a lot of you will forget to recognize or will not recognize when you have a very simple problem. Part A is simply strong acid in water. Okay, there's no buffer system, no weak acid, no Henderson-hasselbalch, no ice table. It's just simply pH equals minus log of the concentration of the hydronium ion. And the concentration of the hydronium ion, if it's a strong acid or base, is equal to the concentration of the strong acid or base that you just added to water. So we just need to find out the concentration of HCl in this system. Okay? So how do we find the concentration of HCl? Well, we start with 0.1 molar, but is that the concentration we end up with in part A? No, because we're taking some of the 0.1 molar and then we're dumping it in more water, so we're effectively diluting, okay? So you can either use the dilution formula to calculate the new concentration, which I'll show you on the next page, or you can kind of do it like a stepwise unit cancellation. So I'm going to show you the stepwise unit cancellation method here. So if you have 10 milliliters, so I'm just going to put it in liters because you're probably more comfortable with that. Okay, and you multiply it by the molarity of the HCl you started with. You can find out how many moles of the HCl that you added. And now but you need concentration to find pH, right? So that's how many moles you added, but now what is the total volume of solution that you have so that you can find molarity? Well, you added 10 milliliters to 100 milliliters, so you have 110 milliliters, okay, or 0.110 liter. So that means the concentration of the HCl that you're working with is 0.0091 molarity. Okay, so you can either do it like this, which I just call unit cancellation method, or on the next page I'm going to show you how you can simply use the dilution formula. Right, if you remember the dilution formula and you have recognized the problem as a dilution, this is an easier way to do it. So the original molarity, M1, times the volume used of that original molarity, which is 10 milliliters, equals the new molarity of the diluted one, which is what we're solving for, times the total volume of the new solution, which is 110. And then you just solve for the new molarity, and of course you should get the same concentration. And then pH, since this is a strong acid, is simply minus log of this new concentration, pH 2.04. So in a system that's not a buffer, just pure water, if we add 10 milliliters of 0.1 HCl, the pH changes from the neutral 7 to 2.4. That is 5 units of pH, which corresponds to 5 orders of magnitude. Okay? So we've changed the acidity by a factor of 10,000 by adding that little bit of a strong acid. So now let's look, if we add the same amount of acid to a buffer system, what type of pH change we have. So now let's look at how that same quantity of HCl contaminant will change the pH if we have a buffer system instead of pure water. First, let's calculate the pH of the buffer system alone before we add the HCl. And as always, that's Henderson-hasselbalch. So really all we need then are the concentration or moles of the weak acid and the conjugate base that make up the buffer system. Plug those values into Henderson-hasselbalch using the pKa of acetic acid, and we find that the pH of the original acetic acid buffer is 4.65. So remember that, and now we're going to add that same quantity of HCl to this buffer and see how it changes the pH. You may remember, I hope, if not, it's worth emphasizing again, when you contaminate a buffer system with an acid or a base contaminant, it's a two-step calculation. The first step is always what I call a mole table. It's a stoichiometry calculation to figure out, first of all, how much of the contaminant did you add, and how much of the original weak acid and conjugate base did that contaminant chew up. And so the mole table kind of looks like an ice table, but units are moles, not concentrations. Okay, so the first thing you want to do is write an equilibrium just like you would for an ice table. And you always have an equilibrium going on between the weak acid and the conjugate base of your buffer system. They go back and forth. That's how a buffer works. In this case, we've added an acid contaminant, and it's a strong one, so I'm representing it with H3O. And you first have to ask yourself, what will this contaminant react with in the buffer? If it's an acid contaminant, it'll react with the base component, the weak base component of the buffer, and that's acetate in this case. They will react to give us the other component of the buffer, which is acetic acid. So we have added 1 millimole of H3O, and that was simply the amount of HCl we added. And just as a reminder, if you go back and read the question, it said 10 milliliters of 0.1 molar HCl were added. So 10 milliliters times 0.1 mole per liter equals 1 millimole. Whoops, 1 millimole. That's where that's coming from. All right, so since there's a one-to-one relationship between the acid reacting with the conjugate base, 1 millimole of the conjugate base is going to be chewed up or consumed by this acid. Okay, and of course, all of the acid's going to react. It's a strong acid, so we're going to end up with 0 acid, and we're going to end up with just a little bit less of the acetate base, just 1 millimole less. It's going to be chewed up by that acid. And remember, the conjugate base, when it reacts with the acid, is going to give you more of acetic acid. So it's going to make 1 millimole more of its conjugate. And so your new levels, your new equilibrium levels of conjugate base and conjugate acid have changed a little bit. They started out 120 and 150 millimoles. They're now 119 and 151. So now that you have the new amounts, you can plug in Henderson-hasselbalch equation, and you're going to see that the pH is 4.64. Now, the original pH of the buffer system was 4.65, I think. Okay, that was original. So it's only changed by 0.01 pH unit, okay, versus 5 pH units if we don't have a buffer. So that's pretty amazing. So here's your turn. And you're probably going to stumble around quite a bit, but that's how you get through the buffer system, okay? So calculate the initial pH of a buffer is part 1. Okay, it's an acetic acid buffer again. And then calculate the pH of this buffer after it's been contaminated with a base. Okay, so the first one is simply going to be using Henderson-hasselbalch, right? Because you haven't contaminated it yet. And when you get to the second problem, you have contaminated it. So the second problem is going to be a 2-step. Remember, one is going to be the mole table, where you figure out how much of this contaminant was added and how it's going to change the ratio of the weak acid and conjugate base. And then after you get the mole table, then you're going to use Henderson-hasselbalch again. So go back and look at the sample I just did if you want. See how you do on your own. Since it's acetic acid, you should remember the Ka, or you can go back and get it. It's 1.8 times 10 to the minus 5 is the Ka value for acetic acid. So I'm thinking you should be able to do the first part of this problem. Write down the equation you're going to use, as always. It's at minimum worth some partial credit. Remember with the Henderson-hasselbalch equation that the conjugate base concentration goes on top. That's the whole key to getting those in the right places. And the weak acid goes on the bottom. All right, pKa is minus the Ka of acetic acid, which is 1.8 times 10 to the minus 5. And the concentration of the conjugate base, the acetate, is 1.25 molar. And the concentration of the weak acid is 1.5. All right, and so going through that calculation, you get the initial pH of the buffer system alone is 4.66. Remember, it should be really close to the pKa value, and 4 is close to that exponent of 5. All right, so now the trickier part is using a mole table to figure out how this ratio of the conjugate acid and conjugate base change after you contaminate it with hydroxide. So that's a mole table. Remember that for the mole table, you're going to have to get these into moles. You can't leave them in concentration for your mole table. So that's the first thing that you're going to have to do. Since your contaminant is a base, hydroxide, it's going to react with the acid component of the buffer, which is acetic acid. All right? And it's going to produce the conjugate, more of the conjugate base, which is the acetate ion. Okay. And so here's what you write to set up your mole table. All right, so you need to know the, let me see, beginning mole value, change of the mole value, and after. All right, BCA table. All right, so the moles of hydroxide, or the contaminant, is what you need to start with. And that, the problem said 10 milliliters of a 0.1 molar solution. And that means that we have 1 millimole of hydroxide. If you'd rather work in moles and convert this 10 milliliters to liters, go for it. You'll get the same answer. All right, so we have 1 millimole of hydroxide. We also need to know the original concentrations of the original mole values of the weak acid and its conjugate base. The problem told us that we had 100 milliliters of the buffer. So 100 milliliters, and the concentration of acetic acid is 1.5 molar. And so we have 150 millimoles of acetic acid to begin with. So that goes in the beginning value for acetic acid. And the amount of moles we have for the acetate ion to begin with. So again, it's the same buffer, so we have 100 milliliters of the buffer, but the original molarity of the acetate solution was 1.25, I think, molarity, which means we started with 125 millimoles of the acetate ion. And so that goes here. Okay, water doesn't matter. Alrighty, so first realize that the amount of contaminant you add is going to react 100%, and whatever that amount goes down here. So you're going to be reacting 1 millimole of the acetic acid away, so you're going to end up with 149 millimoles of acetic acid. And when that acetic acid reacts with the base contaminant, you're going to make more of the acetate. So that's plus 1 millimole. And you're going to end up with 126 millimoles of the acetate. So these are your new mole values for the weak acid and weak base. You do not need to convert them to concentrations to plug them into Henderson-hasselbalch. So plugging the new values into Henderson-hasselbalch, okay, remember the concentration or mole value for the base goes on top. So that's 126 millimoles of the base, 149 millimoles of the acetic acid, and when you put all that in your calculator, you should get a final pH after contamination of 4.67. Look how close that is to the original pH of the buffer. Buffer systems are amazing. So that is your introduction to buffers. Buffers and titrations are bears. You just work a ton of problems, please. That's it for this first lecture, though.